Okay, this is Physics 1C for May 5th. Today we're talking about the concept of self-inductance, RL circuits, and I guess technically there's one other topic contained within here which is we're going to mention. It's worth just highlighting because it's important, which is called back EMF. So those are the main topics today: self-inductance and back EMF and RL circuits. So what is self-inductance? So let's imagine we just take a really simple circuit, okay? So we've got a circuit that contains an EMF source, so some kind of a battery. So we've got a battery right here. And we connect it with wires. And now we're going to leave a switch in here too. So right here we're going to put a switch. And then in our circuit, we're just going to put just a resistor, really. That's it, just a resistor. So it's a really simple circuit. You've got a resistor, it could be a light bulb or something like that, and you've got a battery over here. Now, what we want to talk about is something we've kind of been skipping over for a long time, which is what happens at the moment when you close the switch. So we're going to say in this circuit here that basically the switch is closed at t equal to 0. And then we're going to think about what happens in the system as a result of closing the switch. So we learned in the last chapter that whenever you have a loop of wire and there's current increasing inside that wire, it has the effect of affecting magnetic flux through a loop, right? So let's go ahead and close the switch and talk about what's going to happen here. So we close the switch to here. At this point, there's going to be current that flows through the wire, and the current is going to flow in this direction, in this direction, in this direction, right? That's our current that's going to be flowing through the wire. But since we're closing the switch at this time, we can say that the current is going to try to increase from 0 up to its maximum value, right? So the current is going to increase from 0 up to I, which is going to be equal to the EMF divided by the resistance, right? This is Ohm's law. And that's going to occur over some time. Probably a very small time. The current increases from 0 to this, right? So why does it matter that the current increases? Well, we know that having this current flowing through the wire, it produces an effect that we've been spending quite a bit of time talking about, right? It produces this thing called a magnetic field, right? When I have a current-carrying wire like this, it produces, if I can think about this right, there's a magnetic field inside of this system that points this way, right? And on the other side, it kind of points over here. Up here, the magnetic field, due to these wires, points this way. Up here, the magnetic field points this way, and you kind of get the idea. Maybe the field's a little bit weaker as we get to the center here, but there's definitely going to be magnetic field lines that are going to be going through this loop, right? This is the magnetic field produced by the current in the wire. So the current increases from 0 to this. There's a magnetic field that's produced by that current, right? But, oops, didn't need that. But what does, you guys tell me, what effect does this magnetic field have on the loop from what we've learned over the last 2 weeks? It induces a current, right? And why does it do that? That's right. The magnetic field's increasing, right? When the current increases, the magnetic field that's produced, this is also increasing in time, right? At least it increases up to some maximum value, whatever that happens to be. Right. So the field produced by the current in the loop, it's increasing up to some B max, right? The effect of this is, as I think it was Hunter that said, that means that there's going to be flux in the loop that's increasing. So this means there's an increasing magnetic flux through the loop. And then that has the effect, like the effect of this is by Faraday's law then, right? By Faraday's law. The increase in flux is going to produce an induced EMF. And we call this induced EMF a back EMF. And why do we call it back EMF? Well, Lenz's law told us so many things that go into this. Like, we have to have learned so much stuff to understand what we're talking about right now. And if you're following this, that's very good. If you're not following it, I totally understand. Faraday's law says that you get an induced back EMF, right? And that's because when you have an increase in flux, then you're going to get an induced current that's going to point in the opposite direction of the existing current, right? So maybe we put it on here with a different color, maybe like, I don't know, red maybe? Purple probably. So there's going to be this kind of back EMF that's going to point back this way. Oh, it looks awful, sorry. I'll just call it back EMF. Even better, actually. I should probably call it just the induced current. And that induced current is going to be equal to whatever the back EMF is divided by the resistance. So an induced back EMF, or also a current. This back EMF, it basically opposes the rise in current. Does that make sense? That back EMF opposes the rise in current. And the effect of this is that the current rises gradually, not instantly, up to the maximum value. Oops. Okay, so that is back EMF. It's related to inductance. We'll get to that. But does this make sense to you guys? I'll go back through the process. You close the switch. The current tries to flow in the direction of I. That has the effect of increasing the flux through the loop, which induces a current in the loop backwards in the direction of the existing current. And that induced current will then tend to make it so that the current rises gradually and not instantly. The loop of current literally induces current into itself. It literally induces current into itself by trying to increase the current. Like the throwing of the switch, the current tries to rise. The fact that it's a loop of wire, and due to Faraday's law, means that the rise in current can't happen immediately. Does that make any sense to you guys? Anyone have any questions? It's good. You actually understand this? Okay, because I don't feel like I even understand it very well. I mean, I do, but I've been doing this for years, so it's like, eventually you just kind of figure it out. It's kind of tricky though, right? It's like, yeah. Yeah, what's up? No. That's a really good question, actually. I mean, sure, there's electrons in there that are moving all random places and stuff like that. Wow, that's a really good question, actually. I would say it's more that the net effect of the increase in flux just reduces the circuit's ability to rise the current up to the max level. So instead of some of the electrons feeling a force backwards and some of them feeling a force forwards, it's more like the net force, right? So think about it like when you lift an object, right? Like, let's say you take a bucket, you pick it up, right? You exert a force upwards, and that force has to be at least equal to the weight of the object, right? Would you agree, to lift the object up? So you'd say that your force that you're pulling with is equal to the weight at the very minimum. If you want to pull it harder, you need to pull with the force greater than the weight. And if you do that, and let's say the weight of the object's 100 newtons, and let's say the force you're pulling with is 110 newtons, then the net force on the object is what? It's 10 newtons, right? And I think it's the same thing here. Think of EMF as a force, right? That's why we call it EMF. It's electromotive force, right? So you've got the EMF of the battery pushing forwards, and you've got the EMF that's induced pushing backwards. But the net EMF, at any moment in time, would be the difference between those two, right? So you could say at any moment in time that if we know what the EMF of the battery is, right, that's E, and you subtract from that the induced EMF, at any moment in time that will give you the net EMF. But the thing is that the induced EMF is going to be a function of time, right? I hope that wasn't too confusing, because it's like negative, d phi dt, right? It's the negative change in flux. So that automatically makes it a function of time, and it also is something that eventually becomes zero. Do you understand that? Eventually, this will go to zero over time, because at some point in time, you're going to reach a steady state current system, right? Where there's no longer a change in flux. And at that time, that's when you get the maximum current in the circuit. Does that make sense? At any moment in time before that, though, this induced EMF, basically, this is the back EMF that I'm describing right here. This is the back EMF. This is going to just, start off, honestly, at maximum. At the beginning, it's going to be 12. Like, if this was 12 volts, for example, then at the beginning, the net EMF acting in the circuit is 0. You understand that? After a little bit of time, it rises gradually from 0 up to 12. So, yeah. I was thinking there were electrons going in the opposite direction. Right. It's like the net effect of like 20 electrons going right and 8 electrons going left is like 20 minus 8, or 12 going right. If that makes sense, Tom. I mean, yeah. So that's back EMF. And it's very important when you think about motors in particular. Motors have lots of coils of wire in them. And if you try to turn on the motor, as the motor starts to spin, there's going to be a huge amount of back EMF that's generated, and there's actually going to be an equilibrium that gets registered with a motor, where you actually have like kind of a maximum amount of output power that you can get that is dependent on how fast it's rotating inside. I'm giving you a lot of details here, but my point of saying this is that electricity is a little more complicated than we've been leading on at this point, right? So in the past, we would have said, oh, you close this switch, there's instantly current flowing through the wire. And that's all that's happening. That's what we said back in like chapter 26 and stuff like that, okay? Was you close the switch, the current comes on, that's all that matters. Now that we know that any type of change in current, even if it's a fast change in current, will induce an EMF, we now have to revisit the way that the circuit works. And we find out that there's actually something that matters in terms of this process of turning on the circuit, right? And in the case of motors, it becomes a little more complicated, but the biggest thing to understand is just that, like, when you do have a motor that's running, there's always going to be a back EMF, and the back EMF may actually be proportional to how fast the motor is spinning. Did you guys follow that? The back EMF may be proportional to how fast the motor is spinning, because after all, a motor involves, effectively, God, I wish we did the lab where we made a motor in this class. But a motor involves these coils of wire that are spinning, and the faster they spin, the faster the back EMF is going to happen inside of them, right? Do I need to draw a picture of this? Maybe I should draw it. I don't want to go into too much detail on this. Did any of what I just said make sense? Do you guys have any questions about that? Can I pull a picture of a motor up for you guys real quick? Not a real picture of it. I just want to kind of show... There's images in this book that I could show you. I don't know that they would do justice to what I'm trying to describe. Literature in this section. Well, this is a problem about this exactly. But there's a picture of a motor. That's a picture of a generator. It's basically the same picture. So we looked at this picture last time at the end of class. So that's a generator. A motor is similar in the sense that the way the generator works is that you spin the loop. The spinning of the loop near the magnet has the effect of inducing an EMF, and that causes a current to flow here. The current's like this type of thing right here. Do you guys remember talking about this last time? The way that a motor works is you would replace this device here with a generator, or what? Plug it into the wall basically. And when you plug it into the wall, it has the effect of causing current to flow through here, which places a torque on the loop, which causes the loop to then rotate. You guys understand that? Basically, replace the light bulb with a power source, like plug it into the wall. It will send current flowing through the system, which will then cause the loop to rotate. And that's a motor, basically, right? And what I'm trying to say about back EMF is that the faster the motor rotates, the larger amount of back EMF you're going to get. Does that connection make sense? Ow. Let's stop for a second. It has an effect of creating like a, slowing it down. Slowing it down below what you might expect to get out of it, if that makes any sense. So it's like, maybe you expect it to be rotating at like 120 RPM, but then when you try to turn it up to 120 RPM, you get this huge amount of resistance. And that resistance that you're feeling is effectively back EMF. And so instead of it actually spinning at 120 RPM, maybe it spins at like 88 RPM, where it finds a balance. You know what's really similar to this? A really similar example to this? Imagine you're in a car, right? And you're driving on the road. I may have used this analogy with you guys before, I don't know. You're driving along the road, right? Let's say you're driving at 70 miles an hour and you're on a completely flat road, right? You're not going uphill, you're not going downhill, flat road, driving at 70 miles an hour. Can you cruise at 70 miles an hour without keeping the gas on? Does that question make sense? Like, if you let off the gas when you're moving at 70 miles an hour, will you slow down? Or will you just stay moving at 70 miles an hour? Why would you slow down? Yeah, all those things, all the lossy forces, the things that, like, resistance between the road and the tires, the resistance inside of the internal combustion engine itself, all those things, like, there's resistance to what you're trying to do. So, what do you have to do? Your forward force has to be equal to the backward force, and then you will move at a constant speed, right? And this is basically the same idea, except with EMF. There's going to be an input EMF, and there's going to be a back EMF. The back EMF is like the drag force, or the friction force, basically. Do you guys understand that? So there's going to be like a constant speed that the motor will operate at. Anyway, I'm probably being a little bit too loose with my analogy here. Sorry. But I think that's basically the right one way to think about it, at least, is that back EMF, in a way, is kind of like a friction force. It's certainly a type of resistive force, for sure, that occurs due to this phenomenon of induction that we've been learning about. Okay, does this setup of this make sense to you guys? Okay, so from here, we want to define what self-inductance is, because this effect, this back EMF, is often referred to as a self-induced, because it's a loop inducing it into itself, EMF. Self-induced EMF. Because what would be a non-self-induced EMF? That would be like bring a magnet near this thing and move it in and out of your loop. That would be a externally induced EMF, right? That'd be like an external force, basically, right? But within this loop, we call this a self-induced EMF. Right? And then we define this self-induced EMF in the following way. So we say that this self-induced EMF, we're going to give it the symbol E sub L, and it's defined as being equal to a proportionality constant, capital L, these L's are the same, di dt. It's related to the time rate of change of the flow of current in the system. The quantity L, I'm just going to define for you guys, although we could derive it if you want to, but the derivation would be a little bit like I know what the answer is, and therefore it's not really much of a derivation. This symbol L, okay, is defined like this. It's the number of loops in a coil multiplied by the magnetic flux through the coil divided by I. And this symbol here is what we call inductance. It's often just referred to as self-inductance in different texts. But yeah, and I'm going to draw a picture, and we're going to do a problem so you can understand more about what this equation even means. Wrong words. Self-inductance. A-N-C-E. Or just inductance. Okay? To give you an idea of what this would be, it's like, okay, suppose that I've got a set of coils forming a solenoid or something like that, and I have, you know, some dimensions to this object, right? I know maybe, we're just going to have to do the problem. This picture's awful. We call this self-inductance, okay? And the equation says that self-induced EMF is related to this constant that we call inductance, L, multiplied by the time rate of change of the current in the system. This tells you that the faster that the current changes, the larger the induced EMF is going to be. It also tells you that when the current increases, the induced EMF is going to be opposite. That's what the negative sign means. If the current increases, the induced EMF is going to be opposite to the EMF of the battery. And if the current decreases, then the induced EMF is going to be in the same direction as the battery. That's effectively what the negative sign and the change in current here means. That's too much stuff to write, and I don't want to write it in a large space. I think I'm just going to type what I just said, which is that that's what we call back EMF, right? And then we could also say that the induced EMF is in the same direction when the current decreases. The induced EMF is in the opposite direction when the current increases. It's in the same direction when the current decreases. This is like saying that when you're trying to turn on the current, there's a resistance to that. And it makes it so that it takes time for the current to turn on. When you try to turn off the current, this tells us that the induced EMF is going to continue to drive the current through the system. Does that make sense? Does that make any sense at all? Yeah. So, like, when you try to turn the circuit on, the induced EMF basically pushes against you and stops you from doing that, right? When you try to turn the circuit off, the current is going to kind of try to flow in the same direction. I want you to think about this as something that's really similar to this, although this is a very loose analogy I'm about to give you, so don't take it too far. It's a pretty good analogy, honestly, but it's kind of loose. I want you to think about the following scenario. This is a really simple physics 1A situation. I've got a flat surface. I've got a box on the surface. Let's say the box is really heavy, okay? And let's also say something that we often do in physics 1A, which is totally silly, but whatever. Let's say this is a frictionless surface, right? And let's say this is really big, okay? Let's say that this is like 1,000 kilograms or something. It's like the weight of about a car or something like that. Some big box containing a refrigerator or two or something like that. And let's say you come up to this object and you push on it. Right? Now, it's a frictionless surface, right? So how hard is it to actually get that thing moving? Anything would make it move. You know, how fast is it going to move, though? What would determine how fast it moves? Yeah, how hard you push it, right? So you apply a force, and whatever the force you're capable of applying, you know that it's the only force acting on the object. That force is going to be equal to the mass of the object times its acceleration, right? So basically, you apply a force, and maybe the force you apply, let's say, is like 10 newtons or something like that. Well, that's going to give you a certain acceleration. And now the question is, how long do you apply the force, right? Because the longer you apply the force, the more acceleration the object's going to attain, right? You guys agree? In this case, the acceleration is going to be very small, though. It's going to take a long time to get that up to moving at like a meter a second, right? Because if the mass really is, the acceleration in this case would be, what, like 10 newtons divided by 1,000 kilograms? So what is that? That's like 1 over 100. So it's like 0.01 meters per second squared. To get to 1 meter per second squared, I think you have to push on this thing for like 100 seconds, right? Okay. So, this is going to be a really stupid question, but it's one of those things that, like, I feel like sometimes you have to say things like this to really get people to understand what's going on. Suppose that I replace this with a 1 kilogram object. That looks awful, I'm sorry. So this is tiny, but it's a 1 kilogram object, right? And now I come over here, and it's tiny, so I'm going to push it with my feet instead of, here's the black. So now I'm going to just, like, try to push on this object. Whatever. Okay, so I'm pushing on this, right? And let's say, again, I push with a force, right? And that force is the same force as before. I say it's a 10 Newton force, right? It's going to take much less time to get this object up to speed, right? If I want to get to 1 meter per second with this one, I would say, well, the mass is 1 kilogram, so the acceleration is going to be, I think, 10 meters per second squared, right? So with this object, it would only take 1/10 of a second, right? It would take 1/10 of a second, and then the velocity of the object would end up being about 1 meter per second, right? Whereas with this one, it would take, what was it, 100 seconds? 100 seconds for the object to get a velocity of 1 meter per second, assuming it started from rest, okay? Are you guys on board with this whole comparison here? So what's the biggest difference between these two objects? Obviously, it's their mass, and then in terms of speed, it's that one of them is going to take a lot longer, right? The time. The time is the only difference here, right? You guys agree? It's just the time. The time that it takes for that object to get up to speed is the only thing different between these two objects. Would you guys all agree? Okay, and what's the reason for that? One of them is more massive than the other one, right? So even though at the beginning of this you said that any amount of force will cause this object to move, nonetheless, you would still feel, when you're trying to push on it, you would feel a huge amount of resistance in this case. Would you guys agree? A huge amount of resistance to you trying to push it, right? What is that resistance? What do we call that resistance? There's a name for it. It's not friction. It's not really Newton's third law. It kind of is, a little bit, but not really. Wait, why do you say it's Newton's third law? I shouldn't just completely deny your... because maybe that's a good idea. Why do you say that? That's not the reason. Okay, good. That's okay. That's fine. That's a very... because for a second there, I thought I was thinking about that. It actually made sense. All right. What is the primary reason that you... what is the... I'm trying to answer this question. What is the resistance that you're feeling now? What is that? Is it a force? Is it a force that you're feeling? What is the resistance? You can answer in chat if you want. I'll even write the question down. Like, what is the resistance that you're feeling? What is it? There's only one thing that's different between the two objects, right? It's just the mass, right? What is that resistance you're feeling? By thinking of Newton's laws, you were on the right track. You just picked the wrong one. Yeah, it's inertia. That's exactly right. Did you? What is inertia? Inertia is the idea that an object that is at rest will tend to stay at rest until acted on by a force, and an object that is already moving will tend to move in a straight line forever until it's acted on by some kind of external force, right? So we have an object that's at rest. It has inertia. It has stubbornness, right? It's stubborn. It doesn't want to move. It doesn't want to move on its own. It doesn't have moving parts. It needs something to move it, right? But you go and try to push it, and you're like, wow, there's a huge amount of resistance to what I'm feeling here, right? And that resistance, the word we use for it is inertia. Objects are stubborn. It's hard to push boulders. It's easy to push pebbles, right? So it's not the weight, though. Would you guys agree? Can you guys agree with me that it's not the weight of the object that makes this harder? It's the mass of the object? Nah, it's not just that. It's that mass is what inertia is. These are the same thing. When we describe mass of an object, really what we're talking about is inertia. Yeah, they mean the same thing, because mass is how we measure inertia. But you guys understand it's not a force, right? Like, inertia is not a force. We can think of it as a force in some reference frames or whatever, but in reality, it's just the fact that the object has mass, right? Alright. So now that we have this analogy in front of us, right? I want you to think about, I want you to think about what I just wrote right here, okay? I want you to look at that statement right there. And I want you to think that instead of the word induced EMF, you replace that with the applied force, right? In fact, I'll just... so it's induced EMF, right? It's the EMF is the part that's weird, I guess. I can't complete the analogy right now. The point is that this concept of induced EMF, it occurs due to something that we call inductance. And inductance is in very many ways inertia, okay? Let's see if I can follow this analogy through. Inductance and inertia are synonymous. Inertia refers to mechanical systems, like systems with mass, and inductance refers to, you know, electrical systems, right? So when we talk about an object and it's sitting still, we have to apply a force to make it move. But once it's moving, it will keep moving, right? Once it's moving, it will keep moving. And if you have to apply a force to slow it down, you're going to feel a resistance, right? And that's exactly what induced EMF is. When you try to increase the speed, so current is like speed, when you try to increase the speed of the electrons in the circuit, there's a resistance to your attempt to do that. And when you try to reduce the speed of the electrons in the circuit, there's also a resistance to that, and they tend to flow in the same direction then. I'll repeat that analogy again. So it's like when you try to increase the speed of the electrons, there's a resistance to that. Once the electrons are already moving, if you try to slow down their speed, there's also a resistance to that. Does that make sense? That's what inductance is. Inductance has the effect of making the circuit respond sluggishly to changes in current. Okay, that's usually the type of language that I use to describe this. Okay, so I'll type down here something else, which is that our analogy now is just all of this stuff. I'm going to move this down just a little bit. Inductance makes a circuit sluggish to changes in current. Stubborn, sluggish. Does the word sluggish mean anything to you guys, or do you look at that word and you don't understand what that means? React slowly would be another way to do it. Sluggish, right? Like a slug. Slugs inch along, they're very slow, you know. They take their time, they're stubborn. Just like massive objects. They're stubborn. They don't want to move. And once they are moving, it's hard to get them to stop moving. Alright, does that make sense to you guys? I got these equations up here. We're going to deal with them in a second. We'll talk about the equations, but if you understand this part of it, you really understand more than you really need to know, because the equations are something you'll figure out yourselves, and we'll do some problems and stuff, but understanding the big picture of what's happening is more important. Alright, I'll keep trying to use analogies and stuff to show you guys how this works, and we'll do a little demo here in a second. I think I could do it now. No. Let's do a problem. So let's look at these equations right here. And let's try to solve this problem right here. Not this one. So I just want to copy paste what we just had right there. Those are our equations that we had. And we're going to use these to solve this problem right here. So we have a uniformly wound solenoid with N turns and length L. Assume that L is much longer than the windings in the core of the solenoid is in air. We want to find the inductance of the solenoid, that is to say, this thing here. Oh, I forgot to mention, the unit is the Henry. This is I think it's volt seconds divided by amps. Yeah. Henry is the name of the unit. Alright, we want to find the inductance of a solenoid with N turns and a length L. So we basically have a solenoid, which is basically a bunch of coils of wire, and it has a length of little l, and it has N turns. So the number of turns here is just N. We want to find the inductance of the solenoid. So in order to do this, we have to think about what the flux through our solenoid is going to be. And magnetic flux through an object like this is equal to the magnetic field that's produced in the object, multiplied by the area, and then multiplied by some cosine of an angle between the area vector and the magnetic field. For our solenoid, we're going to say that the area here is A. That's going to be kind of the area of one of these coils right here is A. And for magnetic field, what we're going to use is, well, I don't know if you guys remember this or not. What's the magnetic field of a solenoid? It's equal to mu naught, which is the magnetic permeability constant for air, multiplied by the number of turns per unit length, N over L, and then that's multiplied by the current in the wire, which is I. So let's say that there's a current flowing in this system in this direction, which is I. Yeah, I think we have enough to use this. So from here, we've got our equation that says that L is defined as the number of turns times the magnetic flux divided by the current. That's our definition of what inductance is. So N is just the number of turns. Phi B is what I wrote over here. Let's say that B and A are in the same direction. And then the cosine of the angle is just going to be cosine of 0. And then we divide this by, by I right here. NBA over I. B times A is the flux. And now we plug in the current, or the magnetic field B. So in this equation, the magnetic field is given by mu naught times N over L multiplied by the current. That's the magnetic field. And then we multiply that times A, the area. And then we divide that by the current I. So we end up getting that for a solenoid, the inductance of a solenoid is given by this expression here. There's going to be a mu naught. There is an N squared. And the I's cancel. Oh, there's nothing in the denominator. We're right. So it's mu naught N squared. Oh, there's an L in the denominator. Times the area. And then divided by the length. Something's wrong with me that I couldn't do that simple algebra there. Does that look right to you guys? This is the inductance of a solenoid. Well, it says it right there. The inductance of a solenoid. We'll do a calculation of what it is in part B. So that's A. So if we say that the number of turns is 300, and we say that its length is 25 centimeters, so that would be 0.25 meters, and its area is 4 centimeters squared, which is like 10 to the negative 4. I think it's, we'll do a conversion just in case. So 4 centimeters squared times, there's 100 centimeters in 1 meter. So this is going to be, and then this one only cancel out one of the centimeters, so you have to square this ratio here. Yeah, so it's going to be 4 divided by 100, which I think is going to be 4 times 10 to the negative 4. Okay, let's write that below it, so we don't use up all the space here. So I think this is going to be 4 times 10 to the negative 4. Meters squared, that's the area. So we need to plug all these things into our equation here. So we're going to get that the inductance of our solenoid is going to be mu naught, which is 4 pi times 10 to the negative 7 Tesla meter divided by amp. That's mu naught times n squared, so 300 squared. And then times the area. And then divide by the length. Can you guys calculate what that is for me? And do you see any mistakes that I made? What do you get if you calculate that out? That sounds about right. Unit is Henry. Just checking these units here. What do we get with unit-wise here? One of these meters cancels. You have Teslas over amps. Let's see, what is 1 Tesla? 1 Tesla is equal to, it's a Newton meter divided by an amp, I think. Trying to get to volt seconds over amps. Let's just see what it all works out to be. If you guys can work out the units yourselves. Is this right? Newton FB. I have to write down the equation to remember for myself. FB is QVB. So magnetic field is going to be newtons divided by Q over seconds would be amps. It's Newton divided by meter amp, that's why. I thought that was wrong. Is that right? Tesla is newtons divided by meters divided by amps, yeah. So if we do that, and we look at this one, oops, well, what happened? Newton per meter amp. So if we do this, this whole thing reduces down to Tesla meter over amp would be I'm losing my mind here. How do these units work out? Let's just actually write it all out. Newton equals Q is charge, Coulomb, times meter per second, times Teslas. So you get coulombs per second, which is amp. So this looks right. So you end up getting Tesla meter per amp would be N over meter times amps times meters over amps. Let's check this unit. Did I get that unit right? tempted to look this up on the internet real quick, because I don't have my textbook in front of me right now. Or I could look in the textbook, which is right here. Where's the table of contents? Where's mu naught? Here we go. Tesla time meter divided by amp. There we go. That's correct. Alright. So then this is multiplied by meters squared divided by meters. So this whole thing ends up being, several of the meters cancel. We get something like Newton times meter divided by amp, right? Which is, the numerator is joules. We don't want things in joules. Oh, actually I do, I think in a second. The numerator is joules divided by amp, which is coulombs per second. So this is equal to joule seconds per coulomb. And a joule per coulomb is a volt. Oh! Amps was squared. Whoops. Amps is squared, so this is this times amps. One of the amps you write is coulombs per second, and then joules per coulomb is a volt. There's still an amp left over, so you have volts seconds over amps, which is equal to a Henry. I apologize, that's kind of confusing, but I find the electric units to be kind of confusing, to be honest, and maybe you guys do too, I don't know. But you do get volt second per amp out of this confusing chain of... Be sure you can convince yourself of that. It's always good to be able to do this kind of stuff on your homework. At least it was for me, I don't know. If I confused you guys, it's probably a good time to take a break. Kind of in the middle of a problem though, so maybe we should finish the problem. Any questions? What were we trying to do? Let's circle things back around here. We were trying to find the EMF of a solenoid, and this is what we figured out. Right here. In this case, it was 1.81 times 10 to the negative 4 henries. One thing we could do is we could look at this equation and see what was it that caused that to produce that number, right? And maybe if you wanted to, maybe you want to increase the inductance of your solenoid for some reason, for reasons we'll find out later. Like, I don't know, maybe you need to change the inductance to fix a radio unit that you're using or something like that. Anyway, so what could we have done to make the inductance of the solenoid larger? What do you guys notice? Yeah, the number of loops. That's the biggest thing you could have done, right? It's just make it have more loops, right? So, when we talk about inductance, we say that these things, they have an inductance. But often you're trying to put something like this in a circuit, and you call it an inductor. An inductor basically is really dependent on the number of coils within the system. Okay, so coils matter, also the area matters, the shorter it is matters as well. So if you really wanted to have a really big inductance, you would just have, instead of it being long, you'd have a really short one that's just wound around a bunch of times, right? So you have a whole bunch of ends, but L is just like this tiny little distance here, and A is really big. That would give you a huge amount of inductance. The problem is that this type of object would not quite have this definition of inductance, but I think you get the idea. Because one of the assumptions here was that we have to assume that L is much longer than the radius of windings of the core. So things would change, but nonetheless, these type of objects with a lot of coils in them are what produce inductance. Now, if you've ever opened up any type of electrical device, you may have noticed that there's these little coils inside of it. Those little coils are what are called inductors. They're designed to do exactly this. Alright, the last piece of this is to calculate the self-induced EMF in the solenoid if the current it carries decreases at a rate of 50 amps per second. For this, we're going to use this equation here. We're going to solve for induced EMF, knowing what L is and knowing what di dt is. This is a very simple calculation. The induced self-EMF should be equal to L, which was 1.81 times 10 to the negative 4 henries. And we multiply that times di dt. And there's a negative sign. Di dt in this case is going to be negative 50 amps per second. There's an overall negative sign here. So we say negative 50 amps per second. And we get an induced EMF. I'm sorry. So sorry about that. It's negative 50 amps divided by seconds. So we end up getting the self-induced EMF ends up being about 0.00905. This is going to be volts, because this is volt second over amp times amp over second. You get volts. This would also be written as like 9.05 like millivolts. That's your self-induced EMF. It's a very tiny number, right? It's a very tiny number. 50 amps per second is a huge amount of change in current, too. I mean, an amp of current is a huge amount of current, so this problem is already kind of ridiculous in regards to this. But if you had like a larger version of this, then you'd have more back EMF. Why is that? Because if you have more coils, there's going to be a bigger change in flux, or bigger magnetic field, and bigger change in flux, really. And then that effect is going to drive the EMF backwards. Or in this case, make it keep going, because it's negative. Alright, I think I've talked more than enough for this moment of the class, so I'm going to stop the recording now. If you guys do have any questions, I will take them, and then